On my watch, I don't know whether to say good morning or good afternoon because it's precisely 12.
Just wait a minute.
Then I'll say, just wait just a little bit. Okay, good afternoon. I'm Dr. Michael Kelly. I'm the chair of the Chemical Engineering Department. I'm going to be giving you a bit of an introduction today to your first project for the Engineering 111 class, and it's going to be based upon osmosis. Now, I know that coming out of your background, some of you might know a little bit about what osmosis is, and some might not. So let me see a show of hands and put them up here, not just here like this. Who knows something about osmosis? Oh, you guys have been well prepared by your instructors, I'm sure. They gave you the instructions, presumably, to Google it and find out something about it, because I doubt that you got this in high school. In any event, what we're trying to do in this project is to emulate for you the early stages of something you're almost certainly going to run into as engineers. You're going to have a newly formed concept that you know a little bit about, that you believe might have an application that's going to be worthwhile, and you're trying to not just go with the science and learn about the concept, but you're trying to make something actually happen. And when that kind of a situation comes up, it depends upon your ability to use all the knowledge in your head, plus what you know about the new concept that's just come to you, to plan what you're going to do and then execute it. Sometimes that involves laboratory experimentation, sometimes it involves other things. The one you're going to be doing in this one is sort of laboratory experimentation. And so what we're trying to have you do today is learn a little bit about osmosis, some of the fundamentals, so that you can take that forward and use it to design your own project. Now, it's going to be a 3-week project. Your goal today is only to come up with a design. Now, as often happens in engineering, we're going to put some constraints on you. You're going to have to work with the materials that we make available to you. You can't just go out there and get anything you want, like buy an osmosis thing off the market or something like that. You've got to design something yourself. When you're designing yourself, that means you have to have some idea of what your goal of what you're trying to achieve is. You got to have some idea what the concept is, the technology that's involved, and then you got to use your ingenuity and put something together. Well, that's what we're trying to emulate with this little short-term project. Today, your goal is to come up with a design. If you're fast enough to get going on it and want to actually start building it, that's okay. We have no problems with that. And if any of the instructors of the laboratory want to modify a little bit what I'm telling you right now because you think that's important, please feel free to do that. But what I'm trying to do is to give you the whole of the project. The second week, you're going to actually build that apparatus that you yourselves designed to do the investigation. And you're going to run a test. And probably when you run the test, you'll find it doesn't work quite as well as you thought it was going to. So you might want to make some changes and fix it. So the third week will be your attempt to analyze what happened the first time, decide what you want to modify about what you've done, and do it again, and then compare your results to some equipment that's been put together by our lab technicians that we know works and is going to give nice, consistent results. And then, as we often do for things like this, we're going to award a prize or two to the people that come closest to matching the good stuff. So you can have a little bit of a contest here involved. Hopefully people will find that fun. They usually do. So what I'm going to do today is talk a little bit about what happens in osmosis. The scientific concept it's really old. It was observed back in the 1700s, about 1750 or something like that. But it didn't really become commercially important until the 20th century, when people started learning that they could create polymer membranes that did what osmosis had been doing in nature for a long time. And the concept of an osmosis membrane works something like this. I mean, consider this to be a closed single container here. I'm going to put in it that representing a membrane. What the osmosis membrane is something that will allow the permeation of one of the components, but not the others. We're going to give you one of the easiest ones, one of the most straightforward ones. The component that can transfer across the membranes you'll be working with is water. Pretty much anything that's ionic, like a salt solution, or anything that's a large organic molecule will not go through that membrane. This has been around since mid-50s or somewhere around there. It's been used in commercial applications since then. Some of you may even have found out about the commercial applications. We'll skip on that one. What we're going to have you do, however, is an experiment that looks sort of like this. On one side, we're going to put pure water. And on the other side, we're going to put water plus a salt. Simplest salt that everybody knows about is NaCl, sodium chloride. And that's what you're going to be testing in this experiment. Now what can happen is that the water can pass through the membrane. It's a polymer, it's an organic polymer. It's got micropores, if you want to call them that will allow the water to go through, but the salt cannot penetrate. So, what I'm going to do is discuss a little bit about what the phenomenon is and why it happens. Let's suppose we have this situation right here, and right at the moment it's an absolutely closed container, but I can be like Dumbledore and go like this and make that vanish at some moment. So that's what I'm going to do to start this off. I'm going to put pure water on that side, a salt solution on that side, probably a fairly concentrated salt solution, and then I'm going to wave my magic wand and it goes away. What happens? Who wants to tell me what you think is going to happen? No hands go up. 2 hands go up. A little better. Come on, you guys are better now. Okay, here is the first hand I saw. You come talk.
It would dilute and make it less concentrated?
Yeah, that's an okay way of saying it. What will happen is the salt was a very high concentration here is going to want to diffuse in that direction to where there's no salt. And maybe a little water comes back in this direction. Where does it end up? You end up with a uniform concentration throughout the entire region. And then does anything happen? Well, nothing that's observable happens, but probably still molecules are going to be changing positions. Now we're going to do this again. I'm going to put this back there. For what we just described, where the salt is transferring to make it uniform concentration everywhere, that's a thermodynamic process. There is something called a driving force that makes it happen. The driving force in this case is the difference in concentration between one position and the next. I'll put the membrane back there. Is there, in the same situation, the same driving force between that and that? Hands? How many say yes? Oh, come on. 2 people say yes. There will be a driving force that wants to change things. The driving force says the water goes this way and the salt goes that way. The salt is blocked. It can't go across the membrane. So what happens? The water wants to go to the other side of the membrane to reduce the concentration on this side. That at least is making the driving force a little smaller, so something is trying to happen. So what we are having here is a situation where the rate of transfer, we believe, is dependent on how big the driving force is. If there's a large driving force, you're going to have the highest rate of transfer. If it's almost no driving force, you're going to have almost no rate of transfer, and that's what's happening in reverse osmosis, or in osmosis. Let's suppose that what we now do is to, at time 0, make that happen. And to get time 0, what you really need to do is fill it up really rapidly, so you can call the middle of your filling period time 0, and have the whole time be a lot longer, so that you can ignore the little experimental error in the exact start time. But at time 0, I've got sodium chloride, water solution here, and just water there. What will happen is the water will transfer in this direction. How far will it go? Will it go all the way to all the water coming out of here into there? Because that would reduce the concentration here about as low as you can get it. That's not going to happen. What will happen?
It'll, the water on the right will continue to drive left until it reaches a dynamic equilibrium.
It comes to a point where there's something reducing the transfer rate, something that tries to prevent the water from coming across the membrane. You're exactly right on that. That is called the osmotic pressure. And the osmotic pressure is effectively a pressure between this side and that side that's due to the fact that I've got a salt solution on this side, water wanting to come into it, but pressure here. Let's think about it this way. We start off with the complete closed container, no openings anywhere, and some water comes across this way. Everything is fixed exactly in terms of its physical location. What happens to the pressure on this side? It goes up. I've got the same amount of volume, and I'm putting more molecules into it. I'm putting the water molecules into it. So the pressure here goes up. That means there is now a reverse pressure that's trying to prevent the water coming from this side to that side. This is what I'm talking about when I call osmotic pressure. Now, let's change the situation just a little bit. This is a hint for your experiment. And put a capillary tube above both sides, looking something like that. And I'm going to start this experiment off. Really good experimentation. I'll have exactly the same level of water in both capillary tubes so I can see it. Now at time zero, what's going to start happening? The water is going to start transferring from there to there. But now I've got a place for that water to go. So what does it do? It pushes up that meniscus, and after a while, you'll see this on that side is going up. And what happens on the other side? Simple material balance. It goes down an equal amount. So it'll come down to here. Now, if you make a couple of measurements, you know how long it took to get from the black to the red position, and you know the amount of volume that was transferred, you can get a transfer rate. It will be cubic centimeters of water per second or per hour or whatever kind of units you want to use for it. And it will be caused by the difference in the osmotic pressure due to the concentrations there and there. If the concentration doesn't change very much, the osmotic pressure is going to be pretty much constant. It'll be dependent upon how concentrated it is here. Presumably it's zero there. So you can do this experiment with a low concentration on this side, a medium concentration on this side, or high concentration on that side. And what you would probably expect to see is something like this. If I make a graph of rate versus delta C, where C stands for concentration. I'll put a sodium chloride on it. What would you expect to see? You'd probably expect to see at 3 different concentrations, there, and there, 3 different rates. Well, that's what you're trying to do in the apparatus that you're going to be designing and building and testing. You're going to try to get information that fits into that. We will give you, based upon experiments that have been done using apparatus built by our technicians that we know is consistent, it's the same, so that you can look at all 3 driving forces, delta NaCl is driving force, and get the rates. And then the team that wins is the one that comes closest to what was observed in that rate. Now, what you're going to have to work with is a bunch of materials that we're going to supply for you. By far, the most important single material in there is the holder for the membrane. And I'm going to put something, put it here, like this. There will be a plate, a second plate, looking very much like this. And in between here, there will be a washer on this side, a washer on that side, and then the membrane is held between them. And then there's going to be bolts to screw it down really tight so that there can be no leakage, and you'll have very good sealing. The rest of the apparatus is up to you to design and build. You got to decide what on this side of that piece of equipment is equivalent to that. What on this side of that piece of equipment is equivalent to that. How you're going to put something on top of it. Probably have a couple of different diameter capillary tubes that you could put on top of it, you'll have to know something, or you got to think your way through. What kind of measurements do you need to make, and how are you going to make the measurement? As a hint, you might try putting a ruler behind the capillary so you can see how far it moved in a period of time. And that's the experiment. That's what your goal is going to be, is to create this thing based upon your understanding of what's going on and your design for how you think it can be best built out of the apparatus that's available to you in the class. So, all that having been said, any questions that you have about this? I got one last thing I want to tell you about. Is there any questions on this where we are right now? That means I really did a great job, or you're not quite sure and you don't want to put your hand up. That's fine, doesn't matter. The one other thing I want to point out though is that you can go in reverse. If you pressurize this side higher than the osmotic pressure that goes with the difference in concentration, it will force the water to go in that direction, from there to there. Anybody have any idea what that might be useful for? Purified water in regions where all you have available is salt water, like the Mideast. This is a really big industry, and it's now called reverse osmosis. But it's the same phenomenon. The only difference is you adjust the driving force so that it forces the water to go that way instead of coming this way. The way to do that physically is to really pressurize this side compared to that side, and so you got to design equipment which can handle the pressures, which is big enough to provide a reasonable amount of water so it's useful for something, and the transfer rate is high enough through the membrane that you can make water quickly, and it has turned into a very, very large commercial business. It's based upon understanding the general principle and the fact that somebody did what you guys are going to set out to do, which is to do some experimentation to make something happen based upon an idea. So there's what your goal is going to be. I see all three of the laboratory instructors are here, so I will let you go off and correct any mistakes that I made in my lecture. Oh, and by the way, we are going to post this as a shared file on the shared file for the course in case you want to come back and re-listen to what I just said. Okay? Thank you very much for your attention. I'm glad to see you all. Hope to see you in a couple of years also.
Hi, good afternoon.